thing just to, so we talked about this, that a capacitor can store energy. And the way we kind of thought about that is what a capacitor does is it takes positive and negative charges and separates them, and then that creates energy when you do that. There's like a potential energy. But you can also think that there's energy stored in that electric field. Well, but by the same manner, okay, an inductor can store energy. And it stores energy when there's a current in it, right? Which makes sense. When there's a current in it, it's making a magnetic field. Okay, so we can store energy in electric fields or in magnetic fields. And so the last thing then we're going to talk about is kind of related to this is LC circuit. And so this is an example of a circuit that's going to oscillate, which is, this idea of like an alternating current circuit. So it'll be oscillate in a similar way to like an AC circuit would oscillate. And so we set up a capacitor and an inductor. And so we're going to go through and look at this a little bit. And we're going to assume that our capacitor is like fully charged. That's the sort of situation we're going to deal with. So we assume that our capacitor is fully charged, and there's a switch open, and then we're going to close this switch and try to see what happens. Okay, and how does the circuit respond? Well, what's going to happen is the charge and the current are going to oscillate. So this will be an oscillator, and we're going to show that it's very analogous to a mass on a spring, which is something you probably talked about in 2A at length, right? And so, again, what we can do is look at this, and whenever we have a complicated circuit, the easiest way to kind of look at it is using Kirchhoff's rules. Okay, so we're going to assume that when we close this switch, there's going to be a current. The positive charges will start to want to flow to the negative side. And as they do this, they're going to be causing a voltage in your inductor. And so what we can do then is go through and do Kirchhoff's rules. And so what I'll do is to do that, I'll start down here, and I'll go, from that point, I'll go counterclockwise. And so when I do that, I get negative L di dt, that's the voltage across the inductor, and then plus Q over C, that's the voltage across the capacitor, and that equals 0. So according to Kirchhoff's rules, those two, this will be the sum of our voltages, and those should add up to equal 0. And so typically, when you get to these more complicated circuits like this, then what you do is you try to break these down into a differential equation. So this is probably real similar to stuff you did, again, with a mass on a spring. So the first thing we're going to say is that the current, okay, is going to be negative dq over dt. And the reason it's negative is because your charge is going to be leaving, okay, that capacitor. And so when we talk about Q is how much charge is on that capacitor. So in this case, as the current moves from away from here, you're going to be reducing that Q, okay? And so it might be good to kind of just sort of define that our Q for us is going to be the charge on the top of the capacitor. It'll mirror what happens to the one on the bottom, but we're going to call that there. And what I can do is say, well, then di dt is equal to negative d squared, so the second derivative of q with respect to t. And so if I take this equation here and clean it up a little bit, I get L d squared q plus q over c. And so again, I don't know if you've seen much of these things, but this is a differential equation, which is like a super important thing to us people in STEM and in the STEM field, right? And so our goal here, so we have this Q as a function of T. So this equation gives us a recipe to find out how the charge on the capacitor changes with time. All right, and so you'll go at some point, probably most of you, and take a differential equations class if you haven't already, and that teaches you to go through and sort of solve these differential equations. Now, what's nice is that in general, if you can sort of guess the answer, that works as well. And so here, I'm just rearranging this to kind of make it a little bit more illustrative. And so this is kind of your classic differential equation, if you will, in physics. Okay, so if I just brought the QC term over and then divided by the L, and then just realizing that the L and the C are constants, so I'll put them over there. And so this is my differential equation. So what this is telling me, okay, is I want to find some function Q of t, where if I take two derivatives of it, I get back the exact same function times a negative constant. Okay, so that's how I would think about this. Now again, you'll learn more eloquent ways to do this in differential equations, but I think this is a good way to think about it too. So does anybody know what kind of a function, if I take two derivatives of it, it gives me basically negative of some constant times itself? Anybody? What's that? Okay, so I'm hearing oscillating, sine, cosine. So these are all correct, some sort of sinusoidal function. Now, what I'm going to do is just kind of make a general case. So our sort of general solution can be written, lots of ways, but I'll write it this way here as cosine omega t plus phi. And so these are all kind of unknowns. And then the way that then you do this is you can go through and solve for those unknowns using your initial conditions. But now for us, what does this mean for us? And so first of all, I'd like to say, so we're starting out at the time when Q is maximum. And so I'm just going to write my cosine function like this here. Okay, so this is my Q of t. So at time 0, I'm going to have the maximum value of my charge. And then what I can do is take a few derivatives. So here's Q prime of t. If I do that, I get negative omega a sine omega t. And if I take two derivatives of that, I get negative omega squared a times cosine omega t. And so here's what I was talking about last time. Okay, so if we write the equation this way here, which is a nice way to write it, and then I plug in for that. So my second derivative with respect to time would be negative omega squared a cosine omega t. And then that equals negative 1 over LC times my actual charge, which is a cosine omega t. And so I did, like you guys said, we did exactly what we wanted. So we got this equation here. If I take two derivatives of it, I just get some negative constant times itself. And in this equation over here, I've got basically the term a cosine omega t on both sides. And so I can cancel that out like this and like this. And I get this important relationship here that tells you, so again, to unpack all this stuff, because this is kind of mathy. So we're starting with Kirchhoff's rule. We showed that basically the charge is going to be an oscillatory function. It's going to be a sine function. It's going to oscillate. And better than that, we found that the oscillation frequency is 1 over radical L times C. Okay, by going through and doing this here. Anybody got a question? Like I said, you probably did this in 2A. I do think this is the kind of thing that's good to see a couple times before it really starts to hit home. And then when you do differential equations classes, you'll learn ways to deal with ones that are trickier than this. This is sort of our basic differential equation, if you will, I think. Okay, and so here's how this would look. So here's our sort of pictures here. Okay, and so here would be the charge on the capacitor as a function of time. All right, we know that that's here, so we'll call that this thing here to be Q0. That's the charge at time 0. If I plug in time 0, I get 1, and so that's the maximum. And then the current through the inductor is I max times sine omega t. And again, one thing to be kind of conscious of is the fact that we're defining our current to be negative dq dt. So that's why this works out this way. But we can kind of look at this picture and then just kind of try to interpret this. It's always good, especially when there's so much math, to kind of think of this physically. So what happens is at time 0, right, you've got this circuit that wants to start sending its positive charges around. Okay, so it starts decreasing Q, but this inductor does not like that, and it basically fights it off. Okay, it keeps the current really small at first, and then the current, again, the inductor can't fight it. It can't always fight it, so it just sort of fights it at first, and then finally rises up. And then what happens is when the charge on the capacitor is 0. Okay, so when the capacitor is discharged all of its charge, which in a RC circuit it would be done at that point, in a capacitor and resistor. What's happening is at that point you've got this current in the inductor, and that current can't just stop immediately. Okay, so that current keeps on going in such a way that it charges the capacitor the other way. Okay, so the capacitor started with positive charges on the top, and then it'll end up with negative charges on the top as it sort of charges itself in the other way. And then basically this thing just repeats. And again, what we generally, with this kind of a topic, we try to remind you of the analogies to the stuff you might have talked about in 2A. So it's sort of like a spring and a block. Okay, so you can think about if you stretch a block to some points, this is like the equilibrium position of the block. If you stretch it out over here and let go, that's kind of like the charged capacitor. So the capacitor is charged. It wants to start making current, okay? And then what happens is at some intermediate point, okay, the block is pulled here. You got the maximum velocity of the block. This spring is now starting to push back. And so here, the current has gone through. All the positives have canceled out these negatives, and so the capacitor is neutral. But again, you've got this current in the inductor, and the inductor cannot just stop. Okay, and so the current continues on to the point where you then flip the signage of the capacitor, and that's sort of like this block comes over here and stops. Okay, so sort of velocity equals 0. In this case, it's sort of like current equals 0. And then this thing basically just happens again. So now these positives want to go over to here, and they do it. And again, when they, discharge the capacitor so it's neutral, there's still a magnetic field here that doesn't want to stop. And so you get this oscillation back and forth. Okay, so sort of a mathematical explanation and hopefully a conceptual explanation. But then let's look at some results of this. So here's a kind of, yeah. Well, here, let's just answer it for kicks. Why not? So the idea here is that, so we're saying in this first case, okay, the frequency is 1,000 hertz. Okay, so the frequency that we use in this case over here is 1,000 hertz. And so we want to know is what's the frequency in the other case. And so basically, one of the tricky parts here is that frequency and omega. And it's just one of these things that I know when you first learn this, it can be tricky. But we give omega. And why do we give omega? Well, because omega is what's inside our cosine and sine function. So it's sort of what pops out naturally from our equations, right? But in reality, what we want to do here is in this problem, they're forcing you to kind of think about this in terms of frequency. And so the way I would think about this is, okay, so in the top circuit, it's 1,000. So we know that omega is equal to 1 over radical LC, and that's in the first case. Now, in the second case, how does the capacitance change? We got two capacitors in series, okay? And so if I'm doing two capacitors in series, I'm going to take the equivalent capacitance like this, and this is one that we did a lot, okay? When you got two identical capacitors in series, just like if you have two resistors in parallel, and you add those up, okay, the equivalent becomes C divided by 2. And so what's really happening is if I call omega 1 to be 1 over LC, like so, then my omega 2 will be 1 over radical LC divided by 2. Okay, so the actual value of that capacitance is C divided by 2, which if you clean this up, will end up being 1 over radical 2 times radical LC. And another way to say that is it will be radical 2 times my initial omega. And so omega and F are off by a factor of 2 pi, but the thing is I don't really care about that because I'm asking about how they relate to each other. So basically, the second one will be radical 2 times the first one. If you take radical 2 times the first one, you get this answer of 1400 hertz. Okay? And so this angular frequency is the kind of thing that you really want to remember because this is a useful thing for a circuit like this. All right? And so here's basically any kind of thing that accepts radio signals, okay, any kind of communications device, that kind of thing. What happens is basically there's all these kinds of signals all over the place with different frequencies. And if you have an LC circuit, okay, it's sort of just like when we talked about the idea of resonance, when you, again, back in 2A, when you talked about this kind of stuff. These circuits, if you try to drive them with some frequency that's not close to their resonant frequency, okay, which is this one we just found, you're not going to get much current. Okay, so these circuits really are such that they want to accept this special kind of frequency. All right, and so if you're building something like a cell phone that you want to only accept certain kinds of frequencies and basically block all the other noise out, okay, one way to do it is to have an LC circuit, okay, because again, it's a really finely tuned circuit that only allows, or at least that sort of strongly prefers oscillations right around that angular frequency there, okay. Questions on that?